Absolutely. So from the practical standpoint, the chances that you'll be given a post condition and have to figure out what is the precondition is actually much more practical compared to given the precondition and have to figure out what is the post condition. This is a debugging technique. In other words, you know where the program stopped and did something incorrectly. And you can take a snapshot and say, okay, when the program stopped working, I know that X has this value, 78. It's greater than 78, but it's not supposed to. Okay? So I want to figure out where the program went wrong that causes this problem to happen. Well, this operation by itself, may or may not cause the problem. But I want to find out what can X possibly be before line 81, so I can continue to track this problem backwards until I find out, oh, okay, I took a wrong turn here. I'm not supposed to go to this branch. I'm supposed to go to this branch. So I have to fix the condition of statement so that it is now correct. So I want to go backwards. Okay, so going backward in a program is a very typical thing you have to do in debugging. All right. So given this is the post condition, now we have to figure out what is the precondition. Okay, now it has something to do with inverse functions, but in this case, there's no inverse of squaring something. Okay, in other words, if I give you f of x is x squared, what is f prime of x? Is there a inverse function?
Would that be division?
No.
No.
The square root, right? Most people would think, hey, it's easy. It's the square root, right? Because if I take the square root, it seems to work too. So I would just use sqrt to stand for square root. Okay, so let's do it this way and try to figure out whether that is going to be the solution or not. So we apply f prime to f, apply to x. So that way we have that, and then we have the square root of x times x, which is x. Hey, it works out. Well, we're forgetting one little thing here. Exactly. Yep. It can also be negative because negative x squared is also just x squared. Okay. In other words, in this class, I don't want to go into this part here. It's not 1-to-1 anymore. Okay. There are two possible values that the square of those will still end up at the same place. So given the end result, you can't really go back and say, oh, I know x had to be this particular value, because it can also be the other one. There are multiple answers to that question. So in this case, substitution is not going to work, because substitution is only saying that there's only one way to go about it. But in this case, there are two ways to do it. So in this case, the post condition can no longer be derived mechanically, because we simply cannot use that. So we have to kind of do this more, by hand. Okay. So we have to say this has to be true, but wait, there's another one. The negative square root of x can also be greater than 78. Actually, that's not the case. It has to be. Okay, that's the square is more than 78. So the square root. Oh, okay. Take it back. Sorry. There we go. There we go. That makes sense. Right? Because both of these, okay, that's a precondition, not a post. Okay, I fixed that too. I'll fix it. Okay, there we go. So the precondition, in this case, there are two ways, okay? So even though there's one single outcome, but it can come from two possibilities before line 81. Because the negation of minus the square root of the negation of square root of 78, if you take that square, it will still be 78. So in this case, in the OR case here, oh, forgot about getting rid of the square root here. I wonder you guys look kind of confused. It's like, okay, now it makes more sense. All right, so in this case, x can be less than the negation of the square root of 78. It can also be greater than the square root of 78, because in either case, the square of that x will be greater than 78. So this is one case where the inverse function cannot be applied because there's no one single unique inverse function. Yep.
Since you're going to be getting two answers going up two lines, wouldn't you want f prime of x to be equal to square root of x or be negative square root of x? You show both because you're going to have two answers.
Why? Because there are two answers, they are in a disjunction, meaning that this can be true or this can be true. And that's why they are joined by a disjunction to basically say, well, since we could only confirm this, then the precondition can be either one of these two. Now, technically speaking, the disjunction means it's just a regular or, which means both of these can be true at the same time. But in this case, obviously only one can be true at a time.
When you're first showing the f prime of x, it's a square root of x. Should you show the disjunction there so you know that you're going to be derived by two answers below?
In this case, it's not.
One more line up.
You mean here?
Yeah. Where you're showing that the f prime of x, where you want to show the disjunction there, so you know.
You mean
that
like something more like this? Like that?
Would you want to show that?
But that's
so
not, technically speaking, that's not an inverse function anymore, because inverse function requires is a one-to-one kind of correspondence. This is like one-to-two correspondence. It's technically speaking not an inverse function, because there are multiple things that can map to the same thing. And later on, probably not today, probably in 2 weeks or so, we'll learn how to use the modulus operator. Then it's even more fun, because with the modulus operator, you can see the result of the modulus operation. But when you want to go back to the value before the mod operation, it can be a bunch of values. Okay, but just to make it, so because I mentioned that, somebody is probably already thinking, so what is it? I want to know. Okay, the mod operation, I'm just giving you this a little bit ahead of time. I cannot ask it in exam 1 because this is not a topic before exam 1. But I will just kind of throw this out so that you can start to think about it a little bit here. Okay, so x mod 5 is the remainder of x divided by 5. Okay? Doesn't seem very harmful, doesn't seem very complicated. We're just taking the remainder instead of the quotient, right? Because when I use x/y, it is referring to the quotient of a division. Okay, 20 divided by 5 is 4. 21 divided by 5 is also 4 because 4 is the quotient of 21 divided by 5. This is taking the remainder. 20 mod 5, which is the remainder of 20 divided by 5, is 0. 21 mod 5 is 1 because it is the remainder of the division. Now, if you know the result or the remainder of a division, and I'm asking you what is the dividend before the division, then it's definitely not a one-to-one correspondence, right? Knowing that x mod 5 is 3 means that x can be, it could be 3, could be 8, could be 13, could be anything that fits the form of n times 5 plus 3, n being an integer. So in that case, you kind of your precondition gets a little bit more complicated. Okay, and if this is actually a program that I have to apply this technique, then I will have to resort to using more mathematical symbols to use for all there exists, that sort of thing, because that's the only way to express the precondition. There's no easy way to do it like we are doing in this class. Yep, go ahead.
So, for what you have right here, it's x with the remainder of 5, basically?
It's the remainder of the division, x divided by 5.
Okay.
Because normally we are only interested in the quotient when we talk about division, But there are many occasions in computer science where we are actually more interested in the remainder of a division and not really so much the quotient of a division. Yep.
So you would assign that value to another variable? So
Right.
it'd be like C
To
gets
itself.
X mod 5.
To itself. Okay.
Oh, to
So
itself.
just to carry this one, obviously this is out of the scope of exam one. Okay. So let's say line 67 looks like this. Okay. So we'll say K gets K mod 21. Okay. I'm just picking a value here. And then the post condition, because I'm debugging the program, I know the result of the operation. I want to find out what can possibly lead to that result. So I would say post line 67 is K equals. So this time I'm making a very concrete value. So let's say K equals 4. Okay, the remainder of the division is 4. But what can I say about the precondition? Well, the precondition is K can be 4. Or K can be 25, right? Or K can be 25 plus 21 is 46. Or K can be, well, we can go negative 2. Because the concept of a remainder applies to negative values as well. So in this case, the next one, if I just go to the positive side, is 46 plus 21, which is 67, or blah, blah, blah. Right? Because because 4 mod 21 is 4. 4 divided by 21 has a remainder of 4. Okay, go ahead.
Couldn't you just say K equals 21n in parentheses plus 4?
Then what is n?
Any number.
Well, so now you're introducing an additional thing that is not actually a variable in the program, but it is only useful for the expression of the result. Yeah, you can do that. Was there another hand? Okay. So technically speaking, until you get to CISP 440, you will not see this again. But I think it's a very useful concept. Maybe if you take a math class, you would actually have to encounter this kind of stuff too. So the technical way to express this is basically saying for n in integers, then you say K equals 4 plus 21. I cannot type the mathematical symbol here, so I'm translating everything to the English version. So n is in, okay, fine. It's the element of. Okay, so this is basically saying for all n is an element of the integer set. K equals to 4 plus 21n. And then you have to do a big OR, so you have to specify the big OR operation like this. Or if you prefer, this is the big OR, this is n, this is the big OR, and you have to say, n goes from, just say n is an element of the integer set. Kind of like the summation symbol, except you're not specifying something plus something plus something. You're specifying something or something or something. But this is a general form to basically say this expression is a huge, infinitely big disjunction where